This is the Electricity Homework Booklet, question 6. A student wishes to measure the resistivity of the material of a uniform resistance wire. The available apparatus includes a battery, a switch, a variable resistor, an ammeter and a voltmeter. You are asked to draw a circuit diagram using some or all of this apparatus that would enable the student to carry out the experiment. So here we simply have the battery connected in series with the ammeter, which is in series with the wire and in series with the switch. And secondly, you need to connect the voltmeter in parallel across the piece of resistance wire. The variable resistor is optional depending on the method you choose to follow. So if you were to include it, it could be put in series in this position here. So next you are asked to state the measurements that would need to be made in order to ensure a reliable value of the resistivity. Because they state reliable in the question, this would suggest that you're going to need to refer to repeat readings and finding an average value of resistivity, or you could obtain a set of readings in order to produce a graph. So, first of all, if you choose to change the length of wire, with this method you will need to record each value of the length used, and at each length you would measure the voltage and the current using the voltmeter and ammeter. You could reduce the length that was included within the circuit, and you must also remember to measure the wire diameter. One other option hinted at in the mark scheme is that this lead on the voltmeter could be connected to different positions along the wire, but still maintaining the entire wire within this circuit here. If you chose that approach, the current would stay the same because the whole wire is always part of the circuit, and you would just be measuring the potential difference across a section of the wire. So that would be an acceptable alternative. So if you had followed the method of changing length, then for each value of the length you would find the corresponding resistance using the equation voltage divided by current. You would calculate the cross-sectional area of the wire using the equation pi r squared, and remembering to find the radius by dividing the diameter of the wire by 2. If you state the equation here, this would enable you to calculate resistivity values for each length, from which you could find a mean value. However, it is very good practice to plot a graph. If you choose this approach, you would plot resistance against length. This would give you a graph with gradient resistivity divided by area. So the resistivity would be the cross-sectional area multiplied by the gradient. The mark scheme allowed for either of these final two approaches to be used. Going back to a different method, you could choose to keep the length of the wire constant. If you do that, clearly you just need to measure it once, and you would measure its diameter as before. You could suggest repeating diameter readings. This would increase the reliability of your final value. So for the length you would measure a pair of voltage and current values. You would then need to adjust the resistor, the variable resistor that you would have included in your circuit, and this would give you more values of voltage and current. So finally, to process the data with this alternative method, you would still need to use the equation to calculate resistances, you would still need to calculate the area, and you would still use the equation for resistivity, allowing you to find mean values. If, however, you chose to do a graphical method, you could plot a graph of potential difference against current using your set of V and I values. The gradient of this graph would give you a reliable value for resistance. Finally, rearranging this equation, you can get an expression for resistivity as the gradient times the cross-sectional area divided by the length. Once again, the mark scheme was equally happy with a graphical approach or a mean of a number of resistivity values. Finally, moving on to part B, we have a wire made from tin with cross-sectional area 7.8 times 10 to the minus 9 meters squared, has a potential difference of 2 volts across it. You are asked to calculate the minimum length of wire needed so that the current through it does not exceed 4 amps. If you just think about why it's saying minimum length here, if you were to decrease the length, that would decrease resistance, and decreasing resistance would increase current. So having a minimum length will ensure that the current doesn't exceed a certain value. So looking at the data that you have been given, you know about the potential difference and the current. These two together will enable you to find the resistance of the wire. Then you can substitute into the equation for resistance using resistivity, and substituting in all the values that you know except for the length gives you this data here. Then it's up to you to carefully rearrange, leading to an answer of 0.035 meters.